Alright, so in this video we are concentrating on microcirculation. When we talk about microcirculation, we're really talking about the physiology of the capillaries, and we'll be focusing on Starling forces, and maybe talk a little bit about edema. We're not going to go so much into edema because after this we are looking at renal physiology, and one of the main aspects that we're going to discuss under renal physiology is edema. So the principles on which the microcirculation is based on is really permitting the transfer of substances between the tissue and circulation. So maybe if I write down what is the principle there. So this is transfer of substances. I'm going to name them as substances for now, and then we're going to label the substances between what we are talking about, the tissue and the capillaries themselves. Okay, so what tissues are we talking about? Of course, we're talking from ions to carbon dioxide, to oxygen, hormones, and so on and so forth. Alright, so having established that, we see that there has to be an inlet of the blood, and as well as an outlet. So what happens is, if I may draw, this will be the arterial side. Okay, so it actually goes from arteries to arterioles to meta-arterioles. For now, I just show it as arterioles. Okay, and then we have the capillaries, and in the capillaries we have, of course, the tissue, and in between you have the interstitium. One thing you should note is that, remember, these have muscle, okay, and that is why they're able to, upon contraction of the muscle, we see that these are able to occlude, or they're able to close, so that blood will not go through. But really what happens is that when blood does come, it goes through and comes into this capillary area. And what we're going to concentrate right now on is what are the forces that we see that push and pull the fluid. Okay, now there's several things that you should understand. For example, the fact that the capillaries themselves are one cell thick, and they've got a very sinusoidal characteristic. So though the endothelium is the main cells that have to be penetrated, so to speak, or that have to that guard the coming in or going out, we have a basement membrane as well, but these have gaps. Alright, so they have gaps or fenestrations, and this is a characteristic that is very important in the way that they transfer the substances. Having said that, we want to just go back to where we were coming from. So the first force that you're going to see, so these ones, will be calling them Starling forces. The first force that you're going to see that will push out fluid from the capillary, okay, is one that is known as hydrostatic. Okay, so the first one is the hydrostatic force, and this one is one I'm going to call PC. So hydrostatic force, or PC. Alright, usually we'll put it at 30. Okay, at 30, positive 30. So it pushes fluid from the capillaries out into the interstitium with a pressure of about 30 millimeters of mercury. But we see that there's a second force. You see that within the capillaries you have some proteins that cannot go through these endothelium or cannot go through the walls of the capillaries, and because of that they have an osmotic pool, and this osmotic pool, okay, this osmotic pool I'll label as let me just remove a few of these here. Okay, so I'll label this osmotic pool as oncotic pressure. Okay, so number 2, you have an oncotic pressure, which is the osmotic pool because of the proteins that are inside. So they are pulling in water or fluid to them. So this is also about, let's call it negative 25. Negative 25 because it's pulling water back. So it's got this negative effect. Because what we want to do is to push things to the tissue. So if it's not pushing things to the tissue, then it's got a negative effect. The last two I'm going to talk about are very minute, but they sort of happen, so we want to recognize them. Within the interstitium, we have ions that are there and other solutes. So these solutes or ions also have an osmotic pool, and the osmotic pool, of course, is to them. So this osmotic pool, okay, that is to them, is pulling water from the capillaries to where they are, and it's about 3, yeah, about 3, and because it's pulling water out, so we'll take it as 3. So positive 3 rather millimeters of mercury. So this one is an osmotic pool, but usually you find it as oncotic as well, but I'll call it osmotic pool. Alright, and we'll put it as pi I. Alright, pi I, and we'll say positive 3, whilst the oncotic, we'll say pi C, and we'll put it at negative 25, and the first one was PC, and we put it at 30. The last one, which on my diagram has no space to be, is what is known as the hydrostatic pressure or hydrostatic force, but this one is found in the interstitium. Alright, so in the interstitium you find that there's fluid there as well that may be having a sort of positive, negative push on whatever water is coming in there. Alright, so usually this is at a 0 millimeters of mercury, unless there's a whole amount of fluid there, and then you might record it maybe as a negative 1 millimeters of mercury going on. And so to see what the net influence is of all these pressures, you want to say net filtration pressure will therefore equal all these pressures. So the first one, of course, is positive 30, okay, and then the second one is negative 25, third one is a positive 3, and the last one is about negative 1. So 30 minus 25 will give you 5, plus 3 will give you about an 8, minus 1, approximately approximately it will give you about a positive 7. So you have a pressure outward of about 7 millimeters of mercury. So you have a push of fluid out. All right. So then this arterial side can therefore be known as one that pushes out. What about the venous side? So arterial, again, you will note that it's the one that pushes things out of the capillary to the tissue. What about the venous side? So we see on the venous side a few things that are happening here. First of all, you have the same amount of proteins that are there, but because this side you see that there's less water, the concentration of these proteins would have gone up. Okay, they would have gone up, and therefore you're going to have the protein pool increase to about negative 20. Let me just be certain of that. Negative 28. Okay, and then you're going to have less water because the hydrostatic pressure has already given so much on the anterior side. As it's going this side, you'll find that there's more of a reduction that is going on. So you find that the hydrostatic force or pressure has actually reduced to about 22. So if we just look at this as happening, you can also view the others. Let us see what happens just with these two. So what happens is that just these two is that you have 22, negative 22, and then you have plus 28. So your final is actually a negative 6. Alright, so a negative 6, if we still go on and assume that what was going on in the interstitium is still happening, let's see what is going to occur here. So osmotic pool, alright, osmotic pool will have a plus 3. First one you have minus 3, but then again you have a minus 1 happening because of the hydrostatic force. So you have approximately negative 4. So whichever way you're going to look at, whether you're going to add the other two or just leave it at the first two, you are going to have a net influence of water going back, a suction system, so to speak. So you're going to have a suction system that is happening on the venous side. So the results are that on the arterial side you have a net filtration out of the capillary, whilst on the venous side you have a net absorptive pressure that is going on. So you will also observe a few other things, such as if there are any proteins that do go out, these are reabsorbed by the lymphatic system. So right here you have lymphatic system that works in the interstitium there, and its role is to absorb any proteins that might have been pushed out into the interstitium, okay, so that you have the total interstitial pressure remaining the same. So if there are more here, they will be of course taken up, but by the end of the day the total interstitial pressure will remain exactly the same. So how does edema come in? I'm just going to highlight a few factors. So edema itself is just an accumulation of fluid in the interstitium. So sometimes you find that there's an increase in hydrostatic pressure. And how does increase in hydrostatic pressure occur? So we're just going to draw a few of these. Or let me do this first of all. Let's just have the big one. Okay? So what's going to happen is sometimes we may have an increase in the amount of fluid that is being drained into the capillary. Okay? So this may happen, one, because there is dilatation that is going on here on the arterial end. So we find that there is more of the blood that is being pushed into here. So if there's more blood being pushed into here, it means that the hydrostatic pressure is going to go up. If hydrostatic pressure is going to go up, you'll find that definitely the pressure will be more than 30 millimeters of mercury that is being pushed. Okay, let me not use this arrow for the sake of making sure everybody's on one page. So if that's the case, it will mean that it will be more than +7 or more than +8 at the end of the day. There will be more fluids that are being taken up into the interstitium. How else can this happen? This can happen, I always think, is it dilation? Dilatation. It's still dilation. Yeah, it's a dilate. Dilation. All right. So the next thing that may happen is that we can have the venous side. Okay, the venous side itself can have things happening. You can have thrombosis happening on this side, or you can have let's start with thrombosis. So in thrombosis, you have now fluid coming back, okay, into the capillary, and because it's coming back to the capillary, you will have the capillary hydrostatic pressure increasing, and then you can also have right ventricular failure. So if the right side of the heart is failing, if this is the ventricle, if it's failing, it means it's pushing pressure up into the atria, and if the pressure in here is higher, it means it will push pressure back down into the venous side. Now this pressure in here could increase because the ventricle is not pushing out blood to where it's supposed to be pushing out blood, to the pulmonary system. So if it's not pushing out blood, it means that there is a lot of pressure that is going on in the atrium. And the atrium, it means that it will communicate that pressure to the venous side, and that will also communicate it back to the capillary. And so those things could happen, and then you find a situation where now there is more fluid in the interstitium that should be, and that is known as edema. Other thing that could happen is that we say that we have lymphatics, okay, that are the lymphatic system that sort of draws blood in. If this is clogged by any means, it means that is not happening. And if that is not happening, it means the oncotic pressure within the interstitium increases, and that will have a pool, an osmotic pool. And if it has an osmotic pool, there will be an increase in fluids here, meaning an increase in meaning edema. The other thing that could happen, maybe I just want to make sure that you have a clear understanding, is if you have a high blood pressure going on, high blood pressure will result because there is constriction here. So if there's constriction here, it means there's increase in pressure in the arterial tree. And if there's increase in pressure in the arterial tree, it means there will be left ventricular failure. Yes, because there will be so much pumping that will be required, because the aortic pressure at rest will be at this point much higher. All right. So if there is left ventricular failure, you're really talking about it being due to pressurized arterial system, which could be because of total peripheral resistance increase. Okay. Having said that, I want us now to just focus on what could happen in edema in the pulmonary system. I want us to get to Ganong. Of course, there will be small points for you to read in every component. So in Ganong, I need you to read about pulmonary edema. Okay, is it because of left ventricular failure or right ventricular failure, and how does it really get to the pulmonary component being the one having edema rather than the systemic, which we've just been talking about. In the next video, we'll be talking about venous circulation.